So what is soy sauce? Soy sauce is a traditional sauce that is started in China in 2,500 years ago. It is made from soybean, wheat, salt, and water. During the fermentation, microorganisms help break down the ingredients. Fungi break down the protein and starches, while bacteria and yeast create its rich in umami flavor. The final product is dark, flavorful sauce that is widely used in Asia and many other cuisines. Here is the main ingredients in soy sauce: soybean, koji malt, and also wheat.
Hello everyone, now I will explain the microorganisms involved in soy sauce fermentation and their taxonomy. Soy sauce production involves two main fermentation stages, which is the koji stage and the moromi stage. During the koji stage, the primary microorganisms are the fungi Aspergillus oryzae and Aspergillus zoyzae. They belong to domain Eukarya, kingdom fungi, phylum Ascomycota, class Eurotheomycetes, order Eurotheales, family Aspergillaceae, and finally, at the genus level, both belong to genus Aspergillus. Since both species belong to the same genus, Aspergillus, they share many similar characteristics but differ at different species level. Functionally, Aspergillus oryzae produces amylase and protease, which break down starch into simple sugars and proteins into amino acid. Meanwhile, Aspergillus zoyzae produces glutaminase, which enhances the umami flavor of soy sauce. Next, during the moromi stage, the dominant microorganism is the bacterium Tetragenococcus halophilus. It is from domain Bacteria, phylum Firmicutes, class Bacilli, order Lactobacillus, family Enterococcaceae, genus Tetragenococcus. This bacterium produces lactic acid, which lowers the pH and help prevent the growth of spoilage microorganisms. Finally, the salt-tolerant yeast Zygosaccharomyces becomes active. It is from domain Eukarya, kingdom fungi, phylum Ascomycota, class Saccharomycetes, order Saccharomycetes, family Saccharomycetaceae, and genus Zygosaccharomyces. This converts sugar into ethanol, produces aroma compounds that give soy sauce into its characteristic rich aroma.
Okay, this slide shows the main raw materials used to produce soy sauce and what each of them does during fermentation. So starting with soybeans, this is the main ingredients. So since soybeans are high in protein, they provide the nitrogen needed by the microorganisms. And once they are soaked, they become softer so that enzymes can easily break down the nutrients, which contributes to the umami flavor. And then next is wheat. Wheat mainly supplies starch, so it's the carbon source for microbial growth. And it's also roasted and crushed before fermentation to improve the aroma and make it easier for microorganisms to act on it. And then next we have salt. So salt used at around 70 to 20%. And it helps to control microbial growth by preventing unwanted microorganisms, and it also allows the beneficial salt-loving microorganisms to grow. And the last one is water, which is water acts as the fermentation medium, so it helps dissolve the nutrients and salts, and then it also creates a suitable environment for fermentation. So all these materials have different roles, but together they will ensure that the fermentation process runs properly and produce good quality soy sauce.
I will explain the three main stages of soy sauce production and the biochemical pathway. The first stage is continuous fermentation, which is an aerobic process. The soybean and roast wheat are including Aspergillus oryzae or Aspergillus zoyzae. This was produce enzyme called protease, amylase, and lipase. Protease break down protease into peptides and amino acid, especially glutamic acid, which gives soy sauce its umami taste. Amylase converts starch into maltose and glucose, providing energy for microorganisms. Lipase break up triglyceride into glycerol and fatty acid, which contribute to flavor development. The second stage is Moromi fermentation. The koji is mixed with bread and microorganisms such as Tetragonococcus halophilus and Zycosaccharomyces rosy ferment the glucose. Lactic acid bacteria convert glucose into lactic acid, which prevent the growth of spoilage microorganisms. Yeast convert glucose into ethanol and carbon dioxide. Petrolysis also continue producing more amino acid when alcohol react with organic acid to form ester that creates the characteristic aroma of soy sauce. The final stage is pasteurization. The filtered soy sauce is heated to about 70 to 18 degrees Celsius to eat active enzymes and microorganisms, improving its safety and shelf life. During heating, the Maillard reaction occurs where amino acid react with reducing sugar to form malonatives and flavor compounds, giving soy sauce its dark brown colors and nice taste. Alcohol and organic acid also form ester and volatile aroma compounds, enhancing the final aroma. Finally, the soy sauce is cooled, packaged, and prepared for distribution. In conclusion, these three stages work together to produce soy sauce with its unique color, flavor, aroma, and long shelf life.
Now, I will explain the process conditions involved in producing jalin kicap manis. First is the koji fermentation stage. During this stage, steamed soybeans and roasted wheat are inoculated with Aspergillus oryzae or Aspergillus zoae. The fermentation is carried out under aerobic conditions at a temperature of 30 to 35 degrees Celsius for about 48 to 72 hours, with a relative humidity of 85 to 90%. These conditions allow the mold to produce important enzymes such as protease, amylase, and lipase, which break down proteins, starch, and lipids into simpler compounds. The main factors affecting this stage are temperature, moisture content, and aeration. Next is the Moromi fermentation stage. The koji is mixed with a brine solution containing 18 to 22% salt and fermented under semi-anaerobic conditions at 50 to 30 degrees Celsius for 3 to 6 months. During this stage, lactic acid bacteria lower the pH while yeast produce ethanol and aroma compounds that give soy sauce its characteristic flavor. Important factors here include salt concentration, pH stability, fermentation duration, and microbial balance. After fermentation, palm sugar is added and the mixture is heated to 80 to 90 degrees Celsius. This promotes the Maillard reaction, which develops the dark color, sweetness, and rich aroma of kicap manis. Finally, the product is pasteurized at 70 to 89 degrees Celsius to destroy unwanted microorganisms, improve shelf life, and ensure food safety. Lastly, the yield and productivity of soy sauce depend on efficient enzyme activity, stable microbial growth, controlled salt and sugar concentrations, and proper heating and pasteurization. Poor process control can lead to contamination, inconsistent taste, lower amino acid content, and reduced overall product quality.
My name is Auni Rafana. My metric number is 230248. Once fermentation is complete, the Moromi still needs 4 downstream process before it becomes the sauce we recognize. First, pressing and filtration. The aged Moromi is pressed with a vertical hydraulic press to separate soy sauce from solid residue. Then, filtered to remove remaining suspended solid using a filter aid. Second, boiling and palm sugar addition. The filtered soy sauce is boiled with a high caramelized palm sugar along with the spices. Boiling drives the Maillard reaction between amino acid and sugar, producing dark, syrupy, and caramel aroma. Third, pasteurization and clarification. The sweetened sauce is pasteurized at 70 to 89 Celsius to inactivate microorganisms and enzymes. Then added clarifying agents such as kaolin, diatomite, alum for a clear sauce. Finally, standardization and packaging. Sauce is adjusted to a standard 16.2% salt and 1.6% total nitrogen level. The clarified sauce is then bottled while still warm to maintain sterility.
Next, I'll explain the applications and advantages of soy sauce from the perspective of people, planet, and profit. First, for people, soy sauce is widely used in dishes like rice, noodles, soups, marinades, and even dipping sauce. It enhances the flavor and aroma of food. Since it's naturally fermented, it contains amino acids, peptides, and antioxidants, which give it its rich umami taste and make soy proteins easier to digest. For the planet, soy sauce production is more sustainable because it uses renewable ingredients like soybeans and wheat. The fermentation process uses natural microorganisms, and the leftover soybean residue can be reused as animal feed or organic fertilizer, helping to reduce waste. Lastly, for profit, soy sauce has a high demand worldwide and a long shelf life, making it easy to store and transport. Companies can also produce different varieties such as organic, low sodium, and gluten free soy sauce to attract more customers and increase their profits. Overall, soy sauce is not just a seasoning, but it benefits people, supports the environment, and offers great business opportunities.
So when optimizing traditional soy sauce fermentation, we face three critical roadblocks, which is the microbial contamination, extended duration, and also the sodium paradox. First, traditional open-air methods during the koji stage leave the batch highly vulnerable to unwanted moss and also bacteria, risking spoilage or dangerous methods in formation. Second, the foromine fermentation phase is a massive bottleneck, taking anywhere from 6 to 12 months. It demands extensive storage and also leave the entire batch at the mercy of seasonal temperature shift. Finally, we hit the sodium paradox. While consumers want healthier options, dropping sodium below 50 to 80% severely compromises microbial safety and also ruins the crucial umami profile, making low soy alternative an immense technical hurdle. To solve this challenge, we propose three suggestions. To completely eliminate contamination, we recommend shifting to automated bioreactors. By replacing open trays with enclosed precision control system, we can lock in either temperature, humidity, and also airflow to optimize the enzyme activity. Next, we replace unpredictable wet fermentation with pure starter culture. Utilizing standardized exact microbial strain, guarantee highly reliable fermentation and consistent batch the quality. Lastly, we tackle the extended timeline with the Moromir temperature control. By applying a regulated temperature profile during the bread aging, we can safely accelerate the enzyme activity, significantly shortening the aging stage while fully preserving the deep traditional flavor. That's all.